Good morning. Welcome, everyone. Welcome to this inaugural conference in geometry and physics. Let me just start by introducing our first speaker of the morning. Michael Atiyah is an honorary professor at the University of Edinburgh. He's been professor at Oxford, at Cambridge, and a permanent member of the Institute for Advanced Study. He was Master of Trinity College, Cambridge from 1990 to 1997, Director of the Newton Institute for Mathematical Sciences in Cambridge from 90 to 96. He has been president of both the London Mathematical Society and the Royal Society. He was awarded the Fields Medal in 1966 and the Abel Prize in 2004. He was a student of Sir William Hodge at Cambridge, and his students include Graham Siegel, Nigel Hitchen, both of whom are in the audience, Simon Donaldson, among many others. His collaborators include Raoul Bott, Fritz Herzebruck, and Iz Singer. His contributions to mathematics are far too numerous to list, even in an hour. And Michael has assured me that he has an hour's worth of things to say, and I'm to keep this short. But the highlights include the introduction of topological K-theory, cobordism theory, and other extraordinary cohomology theories. Probably his most influential result is the Atiyah-Singer index theorem, giving a topological formula for computing the index of an elliptic operator. His work starting in the late 1970s is more closely related to the mission of this center and to the theme of this inaugural conference. He began to study the instantons of Yang-Mills theory, leading, among other things, to the celebrated ADHM construction of the instanton moduli space. Since then, he's been a leading force for pushing for the closer collaboration between mathematicians and physicists, and has been enormously influential in developments along these lines in the last 30 years. So it's altogether fitting that I have the great pleasure to welcome as our inaugural speaker at our inaugural conference here at the Simon Center, Sir Michael Atiyah.
Well, thank you, John, for inviting me here, and of course thanks to Jim Simons for providing these magnificent facilities and for starting this center, which I think is going to be of great importance for the development of geometry and physics. I've given my title in advance. You do these things with what you see here, and then you hope afterwards that what you've got to say will fit in. As it happens, it's a perfect title for what I have to say, although that is a much more recent origin than the title. Perhaps I should explain that when this center was getting set up and they were looking for a director, they, of course, sounded out various people, in particular John Morgan. And John Morgan, being a sensible chap, thought he would consult people. He asked me, do I think there's a future in geometry and physics? Is it just a short-term relationship, or is it a stable marriage? Well, I had no hesitation in saying it had lasted 25 years, there was a silver wedding, and it looked like it was going to go on for at least another 25 years, so he took the job. Well, he may have had other advice as well. So, and of course, the famous names that occur at the beginning of the story, we've heard about Chern-Simons theory. Chern is, of course, the father figure in this area, very influential, and sadly not with us anymore, but he and Jim Simons worked closely together, and that's what's led to this building. Amongst the earlier other steps forward of similar importance, I mentioned the Jones-Witten theory, the Jones invariance of knots, and their subsequent interpretation by Ed Witten, and that was the start. These two together were the real main thrust in the connection between topology and physics, and there you see the four villains. Now, my personal story, I want to, from my perspective, I want to start off with where I began. I began off as a student of algebraic geometry in Cambridge, and my teachers were J.A. Todd, shown there, and later on Bill Hodge down the bottom. And I included in there Hamilton, because Hamilton, as you know, was a great mathematical physicist. He did these magnificent things on classical mechanics, Hamiltonians of mechanics, and he also played around with things called quaternions. When I was at school, high school, I had a very enlightened teacher who who taught us about quaternions in my last year at school. I was tremendously enthusiastic. They were beautiful things. We did electromagnetism in quaternion notation. I came to Cambridge. I was terribly disappointed. They didn't know anything about quaternions. They thought they were a gimmick. They taught us stupid things like Grassmann algebras and so on. And I was really disappointed. And I'm delighted that subsequently events have shown Hamilton was right and they were wrong. Now, the kind of predictive geometry I studied has good classical names. Twisted cubics, Klein quadrics, Kummer surfaces, cross ratios, elliptic curves, cubic surfaces with their famous 27 lines, which, by the way, my tutor, J.A. Todd, showed was that the 27 lines on the cubic surface are an instant configuration, and their automorphism group is the Weyl group of the exceptional group E6. Closely related is the plane quartic curve of genus 3, which has 28 bitangents, and the symmetries of that are the Weyl group of E7. So there's some very beautiful things right at the very beginnings of algebraic geometry. They will recur throughout this talk. As an undergraduate, I was so enthusiastic, I even published a paper when I was undergraduate, second year, communicated by J.A. Todd. The title is here, there it is, and it's actually about the relationship of twisted cubics and sets of 3 points, sets of 4, cubic equations, quartic equations. It's a 2-page paper. But when you're an undergraduate and you get a 2-page paper published, it really gives you a kick. And that enthusiastically launched you onto your mathematical career. Now, moving a bit more sophisticated, this is not quite the Veronese surface that is usually used. If you take the projective plane, complex projective plane, have coordinates x, y, z, then if you take, for example, homogeneous polynomials of degree 2 in that, then that will give you a mapping into the complex projective spice space, and the image is called the Veronese surface. But you can do the same thing with cubics. Misprint here, not cubes, cubics. With cubics, and then that maps you into 9-dimensional space. And so you have inside the 9-dimensional space a copy, embedding of the complex projective plane. Now, if you're a geometer, you will know about projection. You're in a space, you take a point, push, you project it down onto lower dimensional space. So what you do, you start with a point on this surface in high dimensions, you project it down. When you project it down, first you get into a lower dimensional space, and the degree of the surface goes down. It starts off at degree 9 because 2 cubics mean 9 points. Then but the point of projection is ambiguous. Where it goes, it gets blown up. Every projection blows up the point of projection, lowers the degree, lowers the dimension. You start off in 9, you can keep going down, 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 until you have to stop somewhere. And the surfaces you get en route are called Del-Pezzo surfaces. And the number n is usually taken to be less than or equal to 8. And abstractly, what you're doing is blowing up endpoints in the projective plane. So what happens to the 2 cycles, the homology of the projective plane? You start off with 1 cycle given by line with self-intersection plus 1. Every time you blow up a point, you add this joint copy of another line with self-intersection number minus 1. So the quadratic form you get after you've done endpoints has 1 plus sign and n minus signs. Now, inside that, there is a distinguished vector in that space, or that lattice, which is given what's called the canonical divisor, given by the vanishing of the zeros of a holomorphic 2 form. And it sits somewhere in that lattice, and as long as n is less than or equal to 8, the orthogonal complement of that lattice, of that vector in the lattice, has a negative definite metric. You see, originally you have 1 plus sign, n minus signs. Depending where you choose your vector, the orthogonal complement may miss the plus signs altogether. And what you get is a lattice of rank n, which is the lattice of the exceptional group En. So some beautiful things right at the beginning of algebraic geometry, and I learnt this sort of thing early on. And many years later, it was used by Waffer and people in connection with the dimensional reduction for string theories. So, algebraic geometry and physics tie up in a very beautiful, simple way at elementary levels. The next interesting thing in mathematics, which I learned later, was concerned with division algebras. We have the real numbers, known for, well, quite a long time. The complex numbers, the introduction of I, probably the greatest single invention in the whole of history of mathematics. What does I mean? What's its significance? And not only you have, when you add I, you can solve quadratic equations, you can solve all equations, and not only do you have algebra, but you have beautiful theory of complex analysis. So the step from the real numbers to the complex numbers is without question the biggest single step taken by mathematicians in their entire history. And then in the 19th century, along comes Hamilton with ideas saying, why can't we go further? Why can't we go to 3 dimensions? And he struggled and struggled, and eventually he found the answer. You can't stop at 3, you have to go to 4. And when you add I and add j to it, you add the product, I times j, k. You add 3 numbers, but you pay a price. You pay the price that the multiplication is not commutative. I times j is minus j times I, and it's not equal to plus j times I. So Hamilton found these beautiful quaternions, which were the next building block in the chain, but at the same time, we entered the area of algebra not being commutative. And this opened up, subsequently, the enormous door of matrix algebras, general non-commutative algebras, group theory. So this was a tremendous highlight in the development of mathematics. And Hamilton wasn't satisfied with that. He was also a mathematical physicist, as his work on Hamilton-Jacobi equations showed. So he actually wanted to write physics in the quaternionic notation. And he spent much of his life doing that. In fact, the second half of his life, he entirely devoted to quaternions. And mathematicians subsequently thought quaternions were really a side issue. That wasn't the way to do physics, for example, because in the quaternions you have 4 plus signs, whereas all physicists know that you have 3 plus signs and 1 minus sign. The Lorentz metric is different from the Riemannian metric. So clearly he was doing the wrong thing. So smart guys. But he did, for example, point out in a beautiful, go and look at his papers, they're lovely. He observes somewhere that if you take these I, j, and k, and you write I d by dx plus j d by dy plus k d by dz, and you square it, you find you get minus sums of the second derivatives. In other words, you get the Laplace operator. And he says in a beautiful note, this must have tremendous repercussions for mathematical physics. In other words, he had discovered the Dirac operator 100 years before Dirac, and he was lying there waiting to be reused. When he was reused, of course, Hamilton's theory really came into its own. And modern physics, of course, has realized that changing the sign from plus 1 to minus 1 is a triviality. You do by something called the Wick rotation, magic touch, and they do it every day. So they're no longer phased by the wrong sign. And, of course, the unit quaternions form the fundamental first non-Lie group, SU2, which is the beginning of all modern physics in lots of ways. So Hamilton really is entirely reinstated as the sort of major figure in the development of mathematics and of physics, and I think he should stay there. And therefore, since I started off as a devotee of Hamilton at school, I was delighted. Now, let's go back to the string. The real numbers, complex numbers, quaternions, unfortunately not commutative, but you still can do with them. And then there is a last ugly duckling, the octonions. Well, when I was at Cambridge, they were called the Cayley numbers, but other people introduced them too. So, as with the standard model, the standard model was due to many people, and because of this disagreement about who should credit it, they called it neutrally the standard model. And the octonions is a bit similar. They use a word which goes beyond 4 to 8 and fits the hierarchy, but left out all the people who contributed to it. So the octonions are an 8-dimensional, so the numbers go 1, 2, 4, 8, instead of, you see, not 1, 2, 3, 4, 5. And I've called them here AI, algebras, A0, well, start, as we do in England, Scotland, counting from 0. The ground floor is 0, not 1. And the octonions don't satisfy, you see, the real numbers really, identity, you start with the identity element of an algebra. Then you have the commutative multiplication, you can weaken it, but you still keep associative multiplication, the associativity law. Those are all present in the first 3, but the last one is the ugly duckling. It doesn't have anything. It doesn't have associativity. It may satisfy some weakened form of it, but it's a bit of a mess. And for that reason, it's not been focused on. But on the other hand, it was known for a long time that you can construct a projective plane, all these different division algebras. You can construct them over the real numbers, complex numbers, obvious. Over the quaternions, you can construct projective planes, but be careful. There is a left projective plane and a right projective plane, because it depends whether you divide by scalars on the left or scalars on the right. They're not really the same. But, surprise, surprise, you can still construct the projective plane over the octonions, even though they don't seem to have any decent properties at all. So the projective plane of the octonions is indication that there's something there you should take seriously. Although, it's another beautiful fact known to people a long time ago, that although you can construct, over the first three of these division algebras, you can construct projective spaces of all dimensions. Also, you can construct general linear groups of all dimensions. And you can do differential geometry that goes with all these dimensions. Real geometry, complex geometry, symplectic geometry. With the octonions, you can construct the projective plane, but you cannot go further. There is no projective three space. And it's not an accident. It's not because you're smart enough. It was known a long time ago that the axioms of algebra, geometry, and projective geometry are intimately linked. And the so-called Desargues theorem in projective geometry corresponds to the associative law. And in 3 dimensions, that Desargues theorem follows from the other axioms. So if you have 3-dimensional projective geometry, it has to correspond to an associative algebra, and octonions are not. So you stop. So this theory is very dull. It's not associative. It has a projective plane, it goes no further. So it's not been really much thought about by most people. And the other ones all lead to 3 big branches of mathematics. Now, the projective planes in topology led to this famous problem of the Hopf invariant 1. Well, that's technical. What it really means is that can you construct manifolds whose homology looks like that of a projective plane in some dimension? In other words, has homology only in the middle dimension with one generator, and the self-intersection of that one is 1. So we know they exist in the dimensions of these algebras. The question was, is there something comparable in higher dimensions, perhaps not given by algebra, but perhaps given by topology? And the famous solution of Frank Adams showed that was not possible. Frank Adams' proof, by the way, took 100 pages, and I subsequently produced a postcard proof by using other methods we'll come to shortly. And to mollify Adams, we wrote a joint paper extending it from prime 2 to the prime p, which is interesting also. Now, so this is the bits of mathematics that right at the beginning have profound implications all the way through. Now let me go up. There is this beautiful object called the magic square, which I only learned about a few years ago working with Jürgen Berndt, who was an expert on these things. And it's not so well known by everybody, and it has real magic. It's called the Freudenthal magic square, but I think a lot of it was due to Jacques Tietz. And these 4 algebras, AI, I call them AI, AJ, you can write in a 4x4 matrix, where you think of the entries of this matrix as corresponding to AI tensor AJ. When you take the tensor product to algebras, you think of somehow the AI as being the left multiplication and the AJ as being the right multiplication. And then you get corresponding Lie groups or Lie algebras. This is corresponding to these. And if you work it all out, you find the following. You find the matrix is symmetrical, as you see, and in the first entry in the top left-hand corner is the orthogonal group in 3 variables. Then you move along and you get the unitary group in 3 variables. Then you get the symplectic group in 3 variables. Now it's 3 by 3 matrices over these different division algebras. And then you get, lo and behold, the first exceptional group, F4. That is the automorphism of the Cayley plane, or octonion plane. Same thing down the side. Then you start looking at the mixed ones, and you get something we notice remarkable, that the last row and column of this matrix gives you all the exceptional groups. Well, G2 has come earlier, and I have left it out, but F4, E6, E7, and E8. And that's really magnificent. In the middle, you get various other classical groups, and they play a role. And you can interpret this. I worked with Jürgen Berndt on the first 2 rows of this matrix, because the first row gives you projective planes. Projective planes, whatever else they are real manifolds. If you've got a real manifold, you can naively try to complexify it. You get a complex manifold of the same dimension. You might only be able to complexify it a little bit, but if you're lucky, you can do the whole job. And you can in these cases. So the second row can be thought of as the complexification of the first row. And then, obviously, having seen that, you should think, well, now go to the next one, third one, that should be the quaternionification. And, well, that's what it is, but it's subtle because of the non-commutative law. And then the last one is, well, it's a bit of a mouthful, it's the octonionification. Well, since the octonions are non-associative, it was hard enough to get a projective plane, it's a bit difficult to understand what that means. So you probably have to resort to algebra. And so you have this beautiful picture of this, where all these things appear. So the first 3 laws of algebra, the identity law, commutativity, and associativity, correspond to the first 3 families of linear groups, which exist in all dimensions. But the last one, the ugly duckling, only exists in dimension 8, but it does give rise to these exceptional groups, which are fascinating objects in their own right, have been extensively used by physicists, are related to beautiful things like the icosahedron. Icosahedron, by the way, is related to E8. The last and most interesting of the groups. Icosahedron is the most beautiful of the regular solids. Now you must ask, has this been applied in topology? Well, very recently there was another famous problem in topology called the K-variant variant 1 problem, a sort of higher order version of the Hopf variant 1 problem. I won't attempt to describe it. And there's been some spectacular work very recently by Mike Hopkins and his colleagues using ideas which have a links with physics, with quantum field theory, and with number theory, with modular forms, and using that and a vast amount of computation which at least parallels that of Frank Adams, they were able to solve this problem with the possible exception they didn't quite know what happened in dimension 128. I should say that this matrix has the properties that the spaces in them, they double in dimension every time you move one step to the right or one step down. So along the top, the projective planes have dimensions 2, 4, 8, 16. When you come down, keep multiplying by 2, and when you get to the bottom right-hand corner, you will find 128. It's quite remarkable, and you can study these in great detail. There's some beautiful geometry, but there's a lot of fascination. So when I saw this result of Mike Hopkins, and he gave a lecture, well, including one at my 80th birthday, I said, you know, surely there's some relation with the magic square. And I spent a lot of time working on it. But then I put it aside because I'm interested in other things. I hope to come back to it. I'm prepared to take substantial odds that this will give you a solution of the problem which is at least as elegant as the solution that I gave for the Adams problem. Oh, wrong button, sorry. Now, the next interesting thing in mathematics were the Clifford algebras. The Clifford algebras came very fast after the quaternions, because in some sense they're a logical sequence. After the quaternions, you can keep adding more ij's and k's and follow your nose, and you get a whole sequence of algebras. The difference is they're no longer division algebras. The division algebras stop at 8, but the Clifford algebras go on indefinitely. Now, Clifford algebras can be thought of in the following way. You have a vector space of some dimension, whatever you like, whatever field you like. Let's start with the real field. And then you have a quadratic form, a non-singular, non-degenerate quadratic form. Over the real numbers, it could be a sum of squares minus sum of another squares, or over the complex numbers, the signs don't matter. And then you form the Clifford algebra. The Clifford algebra is the algebra generated by the, let's say, basis vectors of V, or any vector of V, and you multiply it, and the rule is that if x is in V, then x squared in the algebra is actually a multiple of the identity. And that multiple is the value of the quadratic form on x. That's the definition of the Clifford algebra. Very simple. You need a vector space and a quadratic form. And this can be done over the integers, over the rational, real numbers, complex numbers, whatever you like. Now, in this algebra, you notice two things. Is the equation of the identity that it defines is not degree preserving. On the left-hand side, you have something of degree 2. On the right-hand side, you have something of degree 0, the constants. So this algebra that you get is not graded. It doesn't have a grading. But it has two things. It has, first of all, parity, which is preserved, because both the numbers 2 and 0 are even. And so it has odd elements and even elements. Secondly, it's filtered, which means that when you multiply x by itself, you get things of lower degree, not higher degree. So you can think of the Clifford algebra as having a sequence of subspaces, and if you form the associated graded algebra by first taking one modulo of the next, you throw away things not of the right degree. In particular, you would throw away this fx times 1 because it's of degree 0, you discard it. Then you get the equation for the exterior algebra. The exterior algebra, the famous Grassmann algebras, are when things anti-commute, and they are the limit of this when you make f go to 0. In particular, if you think of just rescaling f by a multiple of f, which I've suggestively called h, and you vary h along possible parameters, then there is a limit when h goes to 0, which really means that you get the exterior algebra, and I call that, and then that corresponds to cohomology theory, because exterior differential forms are what you use in homology, and that you call the classical limit. The other limit, when h goes to infinity, is somehow singular, but you can use some kind of ideas of duality, which exists throughout mathematics and physics, which interchanges the value for large h and the value for small h, and that gives you some insight. So there's a lot of beautiful story here which relates to mathematics and to physics. Physicists have known about Clifford algebras a long time. They use them systematically, and they use all the contents of this story and so they know it very well. Clifford, by the way, was also a very remarkable man. I think in the panoply of mathematical geniuses, he ranks very high. He invented the Clifford algebras, which have had late significance. He also made a beautiful remark forecasting what Einstein did, saying matter is really the sort of high curvature of space, things like that. And he did a lot of other brilliant things too, but unfortunately he was struck down by consumption and died at the age of 37, even though he went to Madeira to recover. By the way, for those of you who are aesthetically minded, he was also a bit of a gymnast. He could do something which I think even Richard Caddison couldn't do. He can go up, hold onto a lamp pole, and stick his legs out horizontally and stay in equilibrium for a long time. That takes a lot of muscle. It was the kind of party trick he would do from time to time. So Clifford is actually one of my heroes too. And by the way, he also was a brilliant speaker. He was much demand as a public speaker on all topics, not just mathematical, regarded as really one of the major figures of that era. When he died in early life, his wife was left with 2 children to bring up, so she had to make a living, and so she took to writing. She became quite a well-known novelist. She was a friend of many of the famous people of the time, including Henry, you know what I mean. And so she wrote a book not long ago about her husband and herself, which is quite well worth reading. It covers the whole mathematical firmament, but also the artistic firmament. Henry James, sorry, was the name I meant. Henry James, in fact, was such a friend of hers that when he died, he left her a considerable amount of money in his will, of which there was speculation. The next big thing in my life, which was alluded to by John, is K-theory. K-theory has lots of aspects to it. The two I point out here, it has this famous Bott periodicity, which is the foundation of K-theory. And the Bott periodicity has a period 8, which is not unrelated, in fact, very closely related to the Clifford algebras and the 8 that comes from the octonions. That's all part of the story. And Raoul Bott, here he is, great man, great friend of ours. I always feel he's looking down on me from above and encouraging me. So I'm sure he would applaud this conference. He was a friend of Jim Simons and Chern. He wrote papers with Chern. And the Dirac operator is the linear operator that was invented by Dirac and that goes with the algebra of Clifford algebras and spinors, and which we used, and is the foundation of the Bott periodicity theorem and lots of things that go with it. The Dirac operator is one of the great discoveries of mathematical physics, although it wasn't discovered by Dirac, but by Hamilton. But that's often the case. But Dirac certainly deserves credit. Dirac, you know, he wrote a beautiful article, which I gave to John Morgan. I would have quoted from it here, but it deserves to be read in full. And I hope he will make it available in some form. It's entirely suitable for this conference. It's given by Dirac in 1939, when he was 36, to the Royal Society of Edinburgh, of which I was subsequently president. That's how I got it, because he was given some prize. And the title is On the Relation of Mathematics and Physics. In that article, which is entirely philosophical and speculative, he says a lot of things. What he says is the most important thing is beauty. You aim to look for simplicity and beauty, but if in doubt, choose beauty. For example, he said, let us compare the Euclidean motion group with the Lorentz group. The Lorentz group is much more beautiful because it's a semi-simple group in modern language, whereas the affine group of Euclidean space is a solvable group in the plane. And of course, it's like more complicated than the Lorentz group, but it's much more beautiful. And that was his view all the way through. You look for beauty, not necessarily simplicity, and that is the aim of all good physicists and all good mathematicians. You should look for the beautiful things. If you find them, you will get eternal salvation. Now, Dirac also says when he discovered his equation, he found it so beautiful. He was terribly, terribly worried. He refused to do any of the further calculations that would check it. He left that to others. He was afraid that any further check might show as false and all his hopes would tumble to the ground. He didn't want to do it himself. He couldn't commit harakiri. So he left it to others who, of course, found his theory stood up brilliantly to cross-examination. But he really believed in the beauty of that theorem. And I'll say a bit more later about the Dirac operator. I could go on for years about the Dirac operator. Much of my life has been devoted to studying the Dirac operator. Now, K-theory has also an interesting relation between cohomology and K-theory, which takes the form of a spectral sequence for experts, which relates cohomology to the K-theory You see, cohomology is graded by dimension. And if you work in differential form, it's given by the exterior algebra, the de Rham complex. K-theory is only graded modulo 2. It's filtered. It's not graded. But if you grade it, you get something very close to cohomology, and in many cases the same. And in any case, there is a spectral sequence that goes from one to the other, which gives you the exact relationship. Now, in connection with physics, it's been clear for a long time that cohomology plays an important role in physics. Periods of integrals and so on turn up all over the place. And it's been clear to me for a long time, and to Graham Siegel, who wrote many papers together, and increasingly to physicists, that K-theory corresponds to quantum theory. Quantum theory, cohomology corresponds to classical theory. And you remember what I said about the Clifford algebras, that you should think of quantum theory as being associated with K-theory. You can make that quite precise in many, many ways, and cohomology is related to classical theory. And so the passage from K-theory, quantum mechanics, classical mechanics, mathematical counterpart is the relation with K-theory with cohomology. And that goes all the way through all the details in great precision. Now, as a sideline, I should say a few words about arithmetic. I'm not a number theorist by any means. But of course, I learned algebraic geometry, and algebraic geometry can be done over different fields, and that gets you very fast into number theory. And I used to go every year to the famous Arbeitstagens of Fritz Hirzebruch in Bonn, and there I would hear talks by Sayre and Grothendieck, and I used to listen to them, you know, as you do to other people's talks, and get a bit of an inspiration, but never really knew the dirty details. And in Grothendieck's language, you have schemes and spectrums of the end and so on. And then, of course, you have, in number theory, you have finite primes, and then you also have the infinite prime. And actually, it's an indication of the ambiguity in life that people don't know whether it's really the prime is infinite or zero, because they call it, it's a characteristic zero field, but they call it the infinite prime. And thereby hangs a deep question, really. Is it zero or is it infinite? Anyway, the theory of arithmetical theory of things, it thinks of all the finite primes going off, and at infinity you end up with the things over the complex numbers, and you end up with analysis, and so on. And class field theory and the Frobenius theory, all this is built into a framework with Adels, in which you have the finite primes and the infinite prime. The infinite prime is where you do analysis, Riemann surface theory. The finite primes, you do finite fields, and it all hangs together in a beautiful way. And by the way, Quillen, who was a colleague of mine in Oxford many years, sadly no longer in good health, and was a student of Raoul Bott, is one, I think, of the most remarkable mathematicians of our time. He did about probably half a dozen really brilliant initiatives, each of which has had tremendous payoff. But he's done them and he leaves them alone and somebody else follows them through. And I can make the list, but I'll just leave it at that. In particular, he developed algebraic K-theory, which is a subtler form of topological K-theory, which has turned out to be very important in modern arithmetic geometry. And there is a spectral sequence that relates that to what's called the Chow ring, which the analog of the spectral sequence that I did with Hirzebruch in K-theory. So this Quillen I put very high up amongst our contemporaries in the originality of his contributions. Now, let's move on to physics. There is geometry, which, if you look in one direction, leads you to algebraic geometry and to number theory. In the other direction, if you go from geometry to analysis, differential equations, you end up with physics. So geometry straddles the border between physics and number theory. This center here is devoted to the part between geometry and physics, but I would suggest to John Morgan that he enlarges his compass and swallows up number theory as well. And of course, those links exist. I want to quote to you what I said, if I can find this somewhere, what I said at the conference. I think it was to recognize Roger Penrose's some birthday or other. I won't go into it. Roger Penrose, who's my contemporary, you can work out which birthday it would have been, he and I were fellow students. We started off as students of Hodge together. But he and Hodge didn't hit it off very well. So he moved sideways and worked with John Todd instead, and drifted by a rather peculiar train of circumstances into theoretical physics. And when I met him many years later, he was already famous for his work on black holes. And then he came back to Oxford, where he became my colleague. And I remember talking to Freeman Dyson when this was happening and asking what he thought about Roger Penrose. He said, well, his work on black holes was really fantastic. But now he does these funny things called twistors. I have no idea what they are. Perhaps you'll find out. And that's exactly what happened. Now, let me read you, if you don't mind listening to this passage, which I wrote, and this is probably, it's probably roughly 20 years ago, or maybe it's his 60th birthday, I don't know. So I'll quote, "As we all know, the fundamental problem that all physicists would like to solve is how to reconcile quantum theory with general relativity. In other words, how to produce a unified theory incorporating quantum gravity. There are many approaches to this goal, and it's not, I hope, blasphemous to make comparisons with the way rival religions offer alternative approaches to God. To the protagonists, the various religions are mutually incompatible and at times distinctly hostile. To the skeptic, the different religious approaches simply cancel each other out, leaving a vacuum. At the other extreme, we have mystics who see underlying commonality in all religious experience and search for some fusion. And as a side remark, mathematicians might note, by analogy, that a combination of oscillatory functions cancel themselves out, but yet leave a few delta functions at specific frequencies. If we now turn to the different approaches to quantum gravity, there are several rival philosophies or religions. The orthodox one is string theory and associated quantum field theory, and here the prophet is Edward Witten. We then have the twisted approach, led by Roger Penrose, and then there is also a newer approach based on the non-commutative geometry pioneered by Alan Kohn. And now as skeptics, we have the hard-headed experimentalists who have little time for theories which deal with monstrously small or large quantities beyond the realm of measurement. On the other hand, there are mystics, among whom I include myself, who hope for a synthesis which embraces aspects of all the rival theories. As a mathematician, I would find it a pity if God had not found some use for all the beautiful ideas that have been put forward. That's what I said 20 years ago, and in fact, I think I have been vindicated. Alan Kohn's non-commutative algebra has beautiful papers which explain, from a particular point of view, how to derive the standard model of theoretical physics, and he also has ideas about how one might prove the Riemann hypothesis, not yet fulfilled, but very promising. Roger Penrose's twisters have been remarkably beautiful in geometry, have been led to an enormous amount of work, out of which things like Simon Donaldson's work is a byproduct. And although the orthodox physicists were a bit skeptical about this, in recent times they have taken it on board. Twistor theory is more and more incorporated into string theory. And finally, we have Ed Witten with strings, who you all know, and who are in particular. All of these are, of course, close friends of mine. I've been associated with many of them for many years. I have great admiration for them, and that's why I'm a mystic and believe in all of them. Now, a word about big and small numbers. By the way, Dirac read a very famous paper. In fact, in this article, he has some very deep things to say about zero and infinity. Now, as we all know, mathematicians have had difficulty with infinity and also with zero over the centuries. You know, the infinitely small in the development of calculus was a big trouble. And so people thought, and then of course the people were slack and rigorous in the 19th century. People like Weierstrass and others solved the problems, and people say that in the 19th century mathematicians tamed infinity. They got it under control, they could use it freely, calculus was well established, everything was beautiful. And zero, well, if you try to divide 1 by 0, you get infinity, and so people at school ask you why you can't do it, and you wave your hands. And but in the history of mathematics, there was, of course, this famous era when Hilbert first put forward the theory that there should be foundations for the whole of mathematics, which are rigorous, you can prove everything. And then along came Gödel, who, as you know, destroyed that vision, showed that this is impossible, there were things you couldn't prove within any system. The whole world came apart. And then even worse came Brouwer. Brouwer, first of all, started life as a topologist who proved the famous fixed-point theorem, which led to existence theorems for differential equations. And then in later life, he recanted it all. He said, it's no use proving an existence theorem if you've got no method of constructing a solution. And therefore, you shouldn't believe in that. The only thing you should believe are the things you can construct. Now, that, of course, is very undermining. It means you can't use analysis, you can't use calculus in a normal form. It destroys most of mathematics. So everybody from Hilbert downward very reluctant to accept this. And the one exception, actually, to his credit, was Hermann Weyl, who loved beautiful mathematics, who one other of my heroes. And he, at the end of the day, said, well, actually, to be quite honest, I think Brouwer must be right. You know, he didn't like saying it, and Hilbert thought he was a traitor. Now, the Brouwer led to what is called the constructivist approach, who only believe in things where you can produce an algorithm which will definitely give you an answer in reasonable time. And nowadays, that is, of course, closely related with questions of computation, and questions, you know, is something computable or not? Logic and computer science go closely together. So a large part of the history of mathematics is encoded in the search for zero and infinity, going back, of course, to the Greeks and Achilles and all that. When I was growing up as a mathematician, the battle had been fought and over, and I didn't pay much attention to the foundations of mathematics. I got on doing it. I thought it was a waste of time arguing about, you know, philosophical questions like this. But as I got older, like Weil, I'm beginning to change my mind. At the same time, physicists have, for a long time, speculated. Modern physics is based on the continuum. You use calculus, you use differential equations, and you know, you get beautiful results. All physics is built on differential equations, as was Newtonian theory. But in recent times, people have probed the very large and the very small. The very large is infinity and the very small is zero in this language. They've begun to realize that, well, actually, is it really true? Can we really believe that space at incredibly small distances continues to be a continuum? We've got no way of checking it because it's impossible ever to get experiments of that scale. And so, you know, what on earth does it mean? And then they start to speculate about other theories and so on. And so one of the languages people use is to say, is space-time granular at very small scale? Well, what does granular mean? Well, it means it looks like sand on the beach. Instead of being a really nice, smooth silk and all that, it's granular. Well, a term which nobody knows how to really means, but this question, and of course, all physicists in their sense really don't believe in the continuum at the very limit, but it's very hard to avoid the continuum. What can you do? How can you develop a theory on granular principles? Well, there is actually, for those of you who like to read it, a very, very thoughtful account of this whole thing in the second volume of the famous textbook on quantum theory by Bjorken and Drell. The first volume is about quantum mechanics. The second volume is about quantum field theory. If I had time, I'd read more of it. But I'll just read one sentence from it. It says, even if there is granularity at small distances, if we are to retain microcausality in granularity of if we are to retain microcausality, the influence of one granule upon the next must be retarded. And that means that instead of doing differential equations, you would have to use retarded differential equations, and those are a bit of a mess. Well, they're a bit of a mess in some sense, sometimes, but not in others. So I want to pursue that. Now, if you follow this through, this idea of granularity at small scales, what that really means is that physicists would say you have an ultraviolet cutoff. You don't really go down to the infinity, you stop short. That means lots of things which would diverge in the limit don't diverge because you cut them off. Well, people quite often try that by hand. You take an integral which diverges at zero, and you say, well, let's take it to epsilon and fiddle around or do some other device. And this is the way physics succeeds in avoiding, not always, but sometimes, the divergences that come with the infinitely small or the infinitely large. The infinitely large, here we call it infrared. Kohn model of the standard model, which I learned a lot about many years ago, and it seemed to be very beautiful in many ways. But only recently, I think I've understood it in a more fundamental way, not looking at this paper, but thinking of it from my point of view. In Kohn's model, the universe, whatever it is, comes in two small sheets, very close together. And what you think of as one point, there are actually 2 points, you know, one up here and one down there, naive, you know, just two parallel disks. And he built his model he has non-commutative algebra involved, and what is his algebra? It's a very stupid, naive algebra. You take the algebra, sum of 2 points, at each point you put a little matrix algebra, something like complex matrices 2 by 2, and you know, you take that as a bit of algebra, and he has machinery for turning non-commutative algebra and doing geometry with it. So you can do with it things like curvature and differential forms and all the normal Yang-Mills theory, and he shows, quite remarkably, that if you take this beautiful, stupid little model and you do it, you get exactly the standard model of physics. But you have to work very hard. You fill pages of calculations. He's very impressed that it works. And I'm very impressed that it works. It looks a bit of mumbo-jumbo. Why did he choose that 2 points? Why did he choose them? Well, all right. Net out, the fact remains, with a very simple little bit of algebra, you plug in the standard machinery, and you get out this very complicated standard model of physics, which is meant to be the real works. So I'm impressed with that, but not fully understanding it. Secondly, in arithmetic, applying the same ideas to the non-commutative algebras that you get from mixing up the addition and multiplication in number theory, what are called adels and edels, he ends up with a framework which might prove the Riemann hypothesis, the ultimate goal of theorists for 150 years. Now, that's not been fulfilled yet, but I understand now, from my point of view, exactly what he's done. I could tell you if you gave me another 5 hours. Now, as you may know, that in one of the big things in mathematics in the previous quarter century were the Weil conjectures, which related numbers of points of curves over finite fields to cohomology. Cohomology theory had to be developed by Grothendieck and Deligne, and finally was successful. And that led to what they called the Riemann hypothesis over finite fields. It was an analog of the Riemann hypothesis, but not over the integers, but over finite fields. And it was an analog in a very rather precise way, and so many people thought, well, obviously what we should be doing is generalizing these ideas from the finite fields to the integers, look for a cohomology theory, and that's been kind of goal, but nobody's got where. One of the important things Kohn did was to develop what he called cyclic homology for associative algebras. If you multiply things in a row, A, B, C, and so on, in associative algebra, you can put the brackets where you like. But you can't necessarily permute them if it's not commutative. In ordinary homology, with things that are commutative, you can apply the full permutation group to all the variables, and with some signs, it's okay. And that leads you to cohomology theories. But Kohn observed that even if things are not, you can't make all permutations, but if you can make cyclic rotations, ABC to CBA, then the following beautiful fact is true. For example, think of ABC as matrices, then you easily check the trace of the matrix ABC is the same as the trace of the matrix CA. Permute them cyclically. And because of that, he developed what he calls cyclic homology, which is true for associative algebra. And that's behind his non-commutative geometry. Very simple idea, very profound, and don't observe, not in significant fact, that cyclic homology, which applies to matrices, is close to K theory and to what I would call quantum theory. Now, going back to retarded differential equations, I was naive enough to take Walker and Drell's idea seriously and say, well, why not try to look at retarded differential equations? You start off on the line, one variable, you write f prime of x plus f of x minus a constant. You know, in other words, you consider the f function evaluated at 2 points separated by a certain distance, which is fixed. The retardation means that what happened a certain distance ago affects you at the present, and retardation has a very important role in electrical engineering control theory. We have delayed signals. Now, when you go from one variable to many variables, and you want to do relativistic theories, you can say, how on earth can I do that? Now, which time direction do I take? In relativity theory, you have a whole cone of directions. And what you need, you observe that the translation operator that translates you by a certain distance is the group element whose infinitesimal generator is differentiation. In other words, formally, if you write exponential e to the d by dt, you're getting translation. So now, if you go to more dimensions, d by dt is really a vector field, first order operator. So in higher dimensions, you're looking for a first order operator which is Lorentz invariant. Now, that's what Dirac looked for, and he found it. He called it the Dirac operator. Only thing is, it has to act on spinors. It can't act on scalars. So you have matrices. So Dirac's big discovery was the relativistic invariance of the Dirac operator. And actually, subsequently, again, there are smart Alex who say, well, you know, Dirac got the right answer by the wrong reasoning. You could just as well take a second order operator, the Klein-Gordon equation, and do it all. And they totally missed the boat. Exponentiating a second order operator gives you a diffusion equation, not group motion. And so it was absolutely fundamental. Dirac was looking for a first order operator, and so I exploited that here. I wrote down this operator, ordinary Dirac operator, plus some constant, times the exponential of minus RD, where R is another constant. You have a mixture of addition and multiplication, if you like. You see, one is in the Lie algebra of translation, the other is in the group. And the parameters K and R. And so I, together with Greg Moore, we developed this as some way of introducing retardation into fundamental physics without destroying all the beautiful symmetry that we like. without destroying Lorentz invariance, covariant invariance, because the Dirac operator is so beautiful, you can define it on curved manifolds everywhere. So throughout the whole geometric approach to physics, you can introduce this notion of retardation without... It's like trying to combine the continuum and the lattice models and doing it, preserving all the symmetry you want. Usually, if you put a grid, you destroy all rotations and symmetries. That's no good. So that's why people haven't tried to do it. But this really is a relativistic way of doing it. Now, of course, it's naive, you might say. Well, how do you know it works? And so on. So anyway, we wrote this paper, which I'll show you in a minute. It appeared recently. And in this, there are two fundamental constants of this theory. There is the number r, which I call the retardation parameter, and the number k, which is some measurement of how important that is. Notice that if you make either k or r go to 0, you get back to the classical case of the Dirac operator. So both of these are deformations away from the Dirac operator. R is the measure of the retardation, k is its strength. And when we applied this to physical systems, we ended up with some rather odd conclusions. First, we found out that R should be quantized. And this, with certain units, you will see that corresponding to the competent wavelength of a particle, if you apply it to sort of neutrinos and things, you get something like 10 to the minus 5 centimeters. This, if you take it seriously, would say that all the fundamental things in nature have masses which are multiples of this one. This one probably is the lowest weight neutrino that we know. So like Dirac proves that every electrically charged particle has an electric charge multiple of the charge of the electron, which is fundamental to physics, we come up here with a rather naive, similar argument about the quantization of mass. Now, the other constant, k, appears in relationship to not the Dirac operator acting on spinors, but if you make it apply to differential forms, then you get to the Ricci tensor, and then you can conclude rather formally, but very vaguely, this number k, combined with Planck's constant, really is the cosmological constant, which is one of the mysteries of physics, and is a remarkably small quantity, and is what's, so to speak, the explanation or reinterpretation of what's called dark energy. So just by looking at this equation, you suddenly find yourself looking at the fundamental questions of physics. Well, none of this is rigorous. It's only clues. But let's leave them at that for the moment. Here is just the front page of my paper with Greg Moore, which I think of as the being alpha and the omega. I gave you my very first paper. This is my last paper, or my last paper as of yet. And they start with algebraic geometry and they end with physics. But you've seen the chain of things that connect them all together is a very continuous chain. Now, the magic square I already alluded to. So this is magic square revisited. There are 4 division algebras, as we've seen. The first 3 are used by Kohn. They lead to associative multiplication. They lead to his standard model. The electromagnetic weak and strong forces, in some sense, correspond to the first, second, and third rows or columns of that matrix. But the 4th row and column, leading from the Octonians and the exceptional groups, very tempting to say they should lead to the 4th force of nature, the gravity. It's obvious. If you're a mathematician who likes beautiful things, like if Dirac was here, he'd say, of course. So we take this seriously. And then you would like to get a combined theory which incorporates all forces of nature and which has the exceptional group E8 appearing, and it has in particular well-defined finite cutoffs, which is related to what Kohn's done, and everything. You should aim for a finite theory, a theory which is totally finite, no divergences, no infinities, and no the zeros. Well, that's the goal. Now, I'm getting to the point of answering John Morgan's question, should he take up this job? Is there a future? Well, let's look at what are the future problems. I've just sketched for you a little bit the future physics. But the famous Millenium Problems given by the Clay Institute, which is each worth $1 million, are listed here as 1 to 7. As you know already, this has been shifted to the wrong place. I corrected oh dear, what's happened here? No. Actually, these aren't meant to be here, but they are here. Anyway, my computer expert misled me. Anyway, here are the Millenium Problems. Now, the Millenium Problems are 7 in number, but I've added the Fermat's last theorem. If it hadn't been solved by Wiles before, it would have been included. And the Perelman solution is, of course, not the Riemann hypothesis, it's the Poincaré conjecture, little slip. Now, well, yeah, he's an eccentric chap. Now, I wanted to suggest, half in jest and half not seriously, to John, that the Simon Center might consider, we've had 10 years of this 21st century, one of the 7 problems has been solved. Progress, but not very fast. So what could the Simon Center do to give it a boost? Well, one thing you might say is, let's say Simon Center might offer some modest sum, I won't offer to give it to you, anybody who can prove that any one of these implies or is equivalent to one of the others. Any link between these things. There are some links which are obvious, and perhaps a big bonus if somebody can prove they're all equivalent. Then, and prove them all too. I think that you might move from the millions into the billions then. Well, the number 5, the Yang-Mills existence of Gaskell, that is what I was talking about up till now. All those ideas would, in particular, lead you in this direction. Riemann hypothesis, I talked about Kohn, is here. So many of the things I talked about are lurking in there. And the number theory, will also. So there are clues that actually these are not totally independent. Now, so here's the list of problems for the Simon Center. I will leave it to John to quantify the rewards. But I suggested a number of things. Prove all 8 in maximum form. Some of them are given a problem, but you can prove much stronger results. For example, Perelman proved the Poincaré conjecture. The whole of the Thurston program comes out as well. Similarly, you might prove the mass gap for Yang-Mills, but you might get the whole of quantum gravity. So there are bigger extensions of the problems. And then finally, you want to develop all this combining arithmetic, geometry, and physics. A special case of all these was, as I mentioned, the Riemann hypothesis. And because I mentioned the fundamental problems being quantum gravity, for ever since Hilbert thought about this thing, it's always been the dream of people that the Riemann hypothesis, which says that all the zeros of the Riemann zeta function lie on a certain line, would follow if you could relate the zeta function to some self-adjoint operator somewhere, and where to look for self-adjoint operators except in physics, and that's been a goal. And people have written down many operators which would give the answer if you could prove that they were self-adjoint. If you had a good physical interpretation, it should be obvious. If something represents a physical thing, it has to have a physical property. So the aim is to find an operator who really is physical, and so Riemann hypothesis follows automatically. Well, in this great world we're talking about, what operator could you have? It has to be what you might call the Hamiltonian of quantum gravity. We don't know what it is, but if you found out, you'd have the Riemann hypothesis. Now, I wanted to finish with quotations, because many things I've been saying have been said by famous people, much better than I can. And so I'd like to go through them with you. Einstein was very fond of quotations, and many of his quotations refer to God, and I'll say more about that in a moment. I want to know how God created this world. I'm not interested in this or that phenomenon, the spectrum of this or that element. I want to know his thoughts, the rest the details. Quantum mechanics deserves much respect, but an inner voice tells me that it is not yet the real thing. Theory gives much, but hardly brings us to the mystery of the old fellow. At any rate, I am convinced the old fellow does not throw dice. That's a famous quotation known to everybody. This is part of Einstein's battle with Niels Bohr and Max Born and so on. And then, of course, they were given in German originally. The Lord is clever, but not malicious. And finally, if God created the world, it was clearly not his main concern to make it such that we understand it. Here is a selection from wider range. Pythagoras, numbers rule the universe. Plato, God is a geometer. Newton, God created everything by numbers. James Jeans, great architect of the universe, now begins to appear as a pure mathematician. And Bertrand Russell, mathematics possesses not only truth, but some supreme beauty. Hardy, the mathematician's patterns are like those of the painter or the poets, must be beautiful. The ideas, like the colors of the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. Alfred North Whitehead, not Henry Whitehead, but his uncle, famous philosopher, and who wrote the Principia Mathematica with Bertrand Russell. Our minds are finite. We are surrounded by possibilities that are infinite. And the purpose of human life is to grasp as much as we can of that infinitude. Good, solid philosophical thought. Albert Einstein again. The most incomprehensible thing about the world is that it is comprehensible. Deep thought there. Don't worry about your difficulty in mathematics. I can assure you mine are greater. And a very unusual quotation from, you see at the bottom, Winston Churchill. I had a feeling once about mathematics that I saw it all. Depth upon depth was revealed to me, quantity passing through infinity and changing its sign from plus to minus. I saw exactly why it happened, but as it was after dinner, I let it go. I hope it's genuine and not a spoof. I can't think why Winston Churchill would have said this, but I found it in the book and I couldn't resist quoting it. And then one that is perhaps pertinent to today, old mathematicians never die, there's 10 to infinity. But I have one final thought for you. I'm not a poet. I can't compete with the poets. But I did once write a short stanza. Jean-Pierre Bourguignon, the IHES, asked me to contribute something to one of their celebratory volumes. So I wrote it, penned it down as that thought came to me. And when I finished reading it, it sounded like a poem. And they translated it into French. You can have a French version. French poetry always sounds better in French, but I write in English. So here it is. Dreams. In the broad light of day, sorry about the S, mathematicians check their equations and their proofs, leaving no stone unturned in their search for rigor. But at night, under the full moon, they dream. They float among the stars and wonder at the miracle of the heavens. They are inspired. Without dreams, there's no art, no mathematics, no life. Thank you.
Thank you, Michael, for that vast tour d'horizon. I think we have time for one or two questions, if anyone dares, so don't go away, Michael.
Okay, delighted to answer questions. Be short, I'll be short in reply. Don't be shy. Okay. Bob.
So I've always, not always, but for a long time, had trouble believing that any physicist could believe that the universe was infinite. And physicists seem to have no trouble with that. To me, infinity is a mathematical abstraction. But how do you feel about it?
Well, I think I didn't have quite time to elaborate, but if you look carefully at what I said, I've come round to the view of Hermann Weyl. The zero and infinity do not exist in the real world. There is nothing infinitely small and there is nothing infinitely big. The theory should therefore involve cutoffs at all points in some natural way, not imposed by, and that is the real world of the real mathematics, which corresponds to the real physics. In physics, I learned from Ed Witten many years ago that if you see a singularity in a physical equation, it's because you haven't dug deep enough into the background. If you go deep enough, the singularity will disappear. So real physics should not have singularities. The number 0 and infinity should be kept away from, and the mathematics, which is in the real world, should also do the same. In that sense, I would approve of Brouwer. I would say that you must have a constructive approach in principle. However, we all know that there is an ideal world somewhere else, and people speculate: is mathematics, where is it? And in the ideal world, you do allow 0 and infinity. You go to a limit. These limits are not in the real world; they are in an ideal world. But in the ideal world, you can do some beautiful tricks. And you go up from the real world to the ideal world, you move around the ideal world, you come down somewhere else, and lo and behold, by analytic continuation, you've got some real facts. So I think that is correct. Both worlds exist, the earthly world, the physical world, and heaven, or whatever you like to call it, where ideal things are true. The mathematician, when he's being a pure mathematician, is an idealist. He lives in the ideal world. A physicist, when he's cavalier about things, he is also in the real world, ideal world. He is doing ideal things. But in the real world, things have to be finite. Everything has to be finite. Infinities don't exist. You banish them from physics and you banish them from mathematics. And I've come more and more to be a firm believer in that. And in that sense, I follow the trail by Hermann Weyl. Hermann Weyl is my hero. Everything I've done in mathematics, I look back and see who did it first. Oh, Hermann Weyl. I missed Hermann Weyl. Well, I saw him once at the International Congress of Amsterdam in 1954 when I was a graduate student. He gave the talk about the field medals. And by the time I got to Princeton in 1955, he just died. I missed him, I missed Einstein, but their memory is still here.
Again, thank you very much. We'll now have a break, and the next talk starts in 40 minutes.